Hello, once more, welcome back to the desk. Servo motors. Yeah, this episode we're going to take a look at the ESP32 board from a previous episode. And today we're going to add this, or one very similar to this, small servo motor. We're going to take a little look at what a servo motor is, outline at least how they work, how you wire up and connect one to control it with software, a little bit about what you can do with one. We're going to take a very brief look at how the ESP32 differs from an Arduino. It's very small, there's just a few lines of code you need to do a little bit differently. It's just something you need to be aware of, and there's a few slight differences in how you connect them. This episode we're only going to look at controlling these things directly. Future episode we'll look at other ways of controlling them. So yeah, here is the board we've been working on in previous weeks, and the only difference is it's got a servo connected. This one is in a 3D printed mount. I'll try and remember to put a link in the description. If you want these mounts, this is on my Thingiverse page. It's a free download, just print them yourself. It's designed to screw like a baseboard here. You drill a little hole through in the middle and you stick a wire in. It's to drive sets of points. That's what that's for. Anyway, let's get on with it. Okay, so what is a servo? Well, in effect, it is an electric motor that instead of going round and round and round, does this. These ones go through 180 degrees, so starts facing that way, ends up facing this way. You can get ones that go through larger angles, through smaller angles. You can get bigger ones, you can get smaller ones. It's basically a magic box that can rotate the arm. You can get them on eBay, AliExpress, Amazon. These are about £3 each on eBay. These are SG90s, which are fairly standard. They're cheaper if you buy them in bulk. It's basically a small box. It's got 3 wires. A small gear wheel on the top. This one's plastic. You can get ones where these are metal. They cost slightly more. There are smaller ones which tend to be more expensive. There are larger ones which also tend to be more expensive. They're used in radio control model aircraft, cars, boats, that sort of thing. Inside, what have we got? Well, let's have a little look. So this is what one of these things looks like from the side. Excuse the not brilliant drawing. We've got a motor. It's not a very big motor, but it works. There's a gearbox, which is why this not very big motor can actually be quite powerful. Part of that gearbox is a sensor. That drives the output spindle, which I say goes to about 180 degrees. And there's some little control electronics. Now this reads the sensor, it reads an input signal, and it decides where the servo arm needs to go, and it turns the motor accordingly. And we have a connector. 3 wires are 5 volt, positive and a ground DC supply. These can take quite a bit of current. Normal operation it's between 100 and 250 milliamps. Less with no actual load on it, as the case is here. If you block it moving, it'll stall. It can draw well over an amp at that point, and it'll get quite hot if it does it. These are not designed to be driven to their stall point. If you're using these to control points, for example, you want them to hold the blades just about in position. You don't want them to be applying a great deal of force because it needs more load. If you want to use that sort of stall control, use a proper motor that's designed to do it. You also want a suitable power supply. You can limit the current if you've got a load of these things by using your code to say only 1 or 2 of them will move at once. And yeah, so what I'm doing here, I'm driving this off the USB port, the PC that's driving this. It's okay because I've only got 1 of them. If I had multiple, you're starting to get a little bit ropey. Quite easy to use an external power supply, however. Yeah, so then you've got the 3rd wire is the control wire. You send in this a control signal, which it references against the ground voltage. Nominally 5 volts, but the SG90 here will function with a 3.3 volt logic signal as well. So like I say, yeah, this is a magic box, rotates an arm through 180 degrees with surprising degree of accuracy. We're going to be looking at 1 degree steps here. These things will go a lot more accurate than that. The higher quality ones are better. You wouldn't necessarily want to use one of these, for example, to drive a turntable. Apart from anything, you'd have to gear it up to go through more than 180 degrees if that mattered to you. They are accurate, they're not that good. but they're good enough. What you can do, however, is move something else. Semaphore, signal arm, I use them for sets of points. All the points on Leopard Street are controlled by these SG90 servos. Level crossing gates. Wonder if we know someone else who's thinking about using level crossing gates for these things. Hello, Ian. Hey. So, how do we drive one? So we'll have a little look at the control signals. This part of the video is actually more for reference, but it's worth understanding what's going on. We're going to use a code library to do all the hard work, so don't scare yourself too much with this one. Control signal, in theory, it's pulse width modulation. So what we have is a little signal like this over time, and the time period by default is 50 Hertz, so 50 pulses a second, so each pulse is 20 milliseconds long. That can be varied. This isn't a true pulse width modulation control system. In there, the logic high and the logic low time matters. Here, only the length of the logic high pulse matters. And the logic low pulse has got to be long enough it can tell the difference between one pulse and the next. 500 microseconds for these little SG90 servos is basically the 0 position or minus 90 position, depending on how you want to use this. So yeah, that's how you set that. You send it a little pulse that does this 50 times a second. Send it a slightly longer pulse, it'll go to its midpoint. Slightly longer pulse, it'll go full scale the other way. Practice, different servos work slightly differently. This is the SG90. A lot of the little servos are very similar. If you're using something else or something more powerful, you need to know what actual length of pulse is. It's often said you want it to be between 1 and 2 microseconds. Well, here it's half to 2.4, but yeah. So yeah, you need to bear in mind that, and the individual servos will also vary. For example, I'm showing this as at plus 90 degrees at 2400 microseconds. It might be 2450 or 2432 or something like that. It depends how accurately you need it. The trick is don't try and use the full 180 degree range. Use the middle 90, plus or minus 45 or plus or minus 60, something like that. So yeah, that's just for information. You don't really need to know that unless you're wanting to control this directly. We'll look at it in another episode a little bit more at how you can use this to get a lot finer control. And this is how you connect things. It's a very simple process. It is literally connect the power, connect the ground, and then connect the servo to a single pin. That's it. You don't need any resistors. You don't need anything else. So, okay. And here we are back at the code. So this is connected. Now, connecting it up, you do need to worry about what pins you use. Now, if you're using an Arduino, you'll see the examples will say, oh, use pins 9 or pin 10. Arduino Unos and Arduino Nanos can support up to 12 of these servos. You'll need an external power supply very, very firmly if you're doing that. The voltage regulator built into a microcontroller is not good for doing that sort of stuff. The ESP32 can support up to 16, and I think if you're using an Arduino Mega, you can get up to 48 of the things on there. So yeah, the reason the code libraries for the Arduino say use pins 9 and 10, internally they take over the pulse width modulation function of those two pins. They use the hardware timer inside. Don't worry about it too much. It's just that's why you'll see libraries say use those two pins. So here I've connected up to pin 13. The primary reason being pin 13 is here, which is quite near the power rail. That was it. That was my reasoning. There is an optional step, which is to put a 100 microfarad capacitor in between the 5 volt and the ground. The ideal place to do that is right over here, right next to the servo. That's obviously not very practical. You could do it at the wiring connection point. You'd need something else in there. I've not done it here, and to be honest, it's working quite happily. So let's have a look at the control software. Right, here's the code we had last time. What we've got in this code is the ability to change our little light, and there's a little interlock, and it feeds some things back. Now, get rid of that. I'm going to look at signal bouncing in another episode. What we're going to do is very, very simply, I'm going to attach the servo in such a way that if the light is green, it'll be in one place, and if the light is red, it'll be in another. I'm not going to go into how the control logic on the servo, the signaling works. We did that in the previous episode. I'm not going to go over that again. So how do we do this? Well, first off, we're going to make the servo move. Okay, so code-wise, we've got the board working. This is as we left it last time. We're going to tag the servo into the little functions all the way down here that actually change the LED state, wherever I put that. Yeah, down here, red and green. That's where we're going to put it. Red state is going to put it in one position, green state's going to put it in another. That's where we're doing this. So how do we do this? Let's just get this servo moving first, because there's two ways of doing this. This is the simple way, just to make sure it works. We bring in ESP32 Servo library. Now, if you go into the library manager, type ESP32 Servo, it's here, you install it, bada boom. You've now got all the code you need available to you. You don't have to write code to worry about sending those pulses out. It just makes life really, really simple. What we then need to do is say we're using a servo. So I'm going to come down here in the global variables at the top, and I'm going to create a servo. This is pretty similar to the Arduino Uno. You just need to check the library examples online for that. It's there. You're just going to include servo.h. This just copy and paste another file in effect. It's a library file. We'll be using a lot of these. So we've created that. What we now need to do is configure the servo, and for the ESP32, this requires me to add these lines here. The Arduino Nano and Arduino Unos don't need those lines. This is purely telling the computer we want to use the pulse width timers on here. I think there's 4 of them, and they can control 4 servos each. Different ones talk to different pins, so basically by grabbing them all, we don't have to worry about it. What we're then going to do is say, I want this servo to work on 50 Hertz. If you're using the Arduino Uno library, the library sets the frequency. Here we can do it on individual servos. They're all going to be the same, so it's not really a problem. We then need to configure the servo itself, where we do this. And because we've done that, I need to also go in and tell it where it has been connected. And what this line here is doing is saying attach the servo to that pin. There's its minimum, there's its maximum. If you remember those are from the timing diagram we looked at just now. There we go. That's now configured. And literally, all we need to do now, I'm going to scroll down to where I can find the code I need on this. We come down into here, and we're going to say, in this line here, make the servo go to 45 degrees. And in this one here, make it go to 135 degrees. And that's it. There's no more code required to make this work. So let's upload that and let's see what it does. I'll just clear that bit out. Upload. And I will press the appropriate button so that when it's ready, it will actually upload. It goes through the build process and then uploads. And I'm going to hold this way so you can see the arm on the thing. Ooh, there we are, it's moved. Signal's red, we're at that position. Go green, it goes over there. Comes back. You might be able to hear it. Hold up to the microphone. But if all you care about is making the servo move, that's actually it. That is literally it. You could connect multiple ones on different pins and you could control them in exactly the same way. Now that's all well and good. But if you had that controlling points, you might not want it to move that fast. And part of the point in using servos instead of solenoids is you can make the things move more slowly. Same with a signal arm. You might want it to move more gently. Or anything else you can connect to. I mean, crossing gates. You don't want them moving like that. You could use that to flick something. You might want that for some functions. But how can we make that move more slowly? Now, this is actually quite simple. It can be made complicated. For example, if you want to use a constant travel time regardless of distance. So going from this position to that position, I want that to take a second. But from here to the midpoint, I want that to take a second. From there to slightly further over, I want that to take a second. You can do it. We're not going to do that today. We're going to look at how to do this more simply. Now, to start with, we need to change how we're going to control this a little bit. We need a little bit more information now. So what we're going to need is, we are going to need to know where are we now. And this is the angles that we're going to write. You can write microseconds directly. I'm not doing it. This one is where do we want to go? Because we need both of those. We need to know, because we're going to move in 1 second, 1 degree increments. We need to know how much time do we want between those increments, and this is in microseconds. So I'm going to say we're going to move 1 degree, wait 25 microseconds, move another degree, 25. Yeah, you get the idea. And we also need to know when did we last move. This has all been done as global. This would make controlling multiple servos a little bit more difficult. Another episode we're going to look at how you create a software class to do all this sort of stuff. We also need some generic timing information, which is stuff code I tend to use fairly regularly. So uint32, these are 32-bit numbers. This is what the internal timing system on these chips use. If you're using a Pi Pico, you can do this in 64-bit numbers. Their system's a bit more accurate, but there you go. So T now is the time now. So on every loop iteration, what time is it? T elapsed is how long is it since the last loop went through. And T old is just where we store what the previous time was. So when we get into a loop, we know what we're doing. We have the same configuration code. We don't need to do anything else there. Now we come into the loop, and the first thing we need to do is that timing code. So what I'm going to do is that. And this here uses this millis function, and this says, right, the time now is equal to whatever this function returns. And this is the number of milliseconds since you last reset the microcontroller. It's not the actual time, it's just the time since we switched the thing on. So I'm going to go into that, and I'm going to say, well, the time elapsed is the difference between that and whatever the old time was. That starts as 0. So the first time you run this, you get however long it took the thing to switch on. And then at the end, we say, well, actually, the old time is now whatever it is now, ready for the next loop. And that's that. And now we're going to come down here, and instead of saying, where are we? Let's find the numbers here. Instead of saying this my servo right, what I'm actually going to do is set the target position instead. Now this doesn't do anything at the moment, but what this is saying is when I press this button, that is the position I want the servo to be in. It's not going to go there, but it's there. And then what we're going to do down here is we are going to create a little loop which is going to run for the servo. And this goes here. So I'll put the braces in below it. So what this is saying is every time we go through the loop, are we where we want to be? So does the current position equal the target position? And if it doesn't, so in this case not, we're going to do this little loop in here. This exclamation mark is not equal to. So if the current position is different from the target position, do whatever's in this little bit. Which means if we are where we want to be, we don't do anything. We're then going to have another little one, like this, and this says, if the time now less the delay time is greater than the time we moved last time. So this is basically, are we due to move an increment? If The current position might not be the target position, but it's too soon to move, in which case we're going to do nothing. But if in here we need to move, so what we're then going to do is say, and this is all fairly straightforward stuff when we get into it. If the current position is less than the target position, this means the current position is too low. What we need to do is make our current position a little bit bigger. And this plus plus is equal to, say, it's an increment operator. It's saying current position equals current position plus 1. It's just a shorthand way of doing that. The alternative to that is obviously we're too far, and if we're too far, we're going to go the other way, and we're going to do that, which again is a decrement operator. Now at the moment, we haven't actually done anything. So what we're now going to do is tell the servo to go to the current position. We've started out with where it is. We've now adjusted where it is to where we want it to be, and we're saying, right, do it. And then the final little bit of code we need to add is that bit to store when we did it. This is so we know next time how to do. Let's upload this and see what happens. So again, I shall press the magic button. I shall let this run. And then release that, and for some reason it's decided not to upload it. At this point there was several minutes worth of prattling about trying to get this to work. It did eventually upload. I'm not entirely sure why. I'm going to investigate that a little bit more thoroughly. However, you don't need to see all of these attempts in real time, so we'll just click back to when it worked. Right, okay, after multiple attempts at getting that to work, eventually it worked. Yeah, I'm not sure what the cause of that was. Anyway, if it happens again, I'll keep having to play. Anyway, here we are. So, let's see how this works. Seems it's a bit better. Go back again. And that's about it for a single servo. You could set the positions and what have you. So, yeah. So, conclusions. This episode we've seen what a servo is. We've had a little look at the principle of controlling one. We've seen how to use a code library to simplify the operation. We've seen how to connect a servo. We've seen how to make it move quickly. We've seen all sorts of problems trying to upload code to an ESP32. We've finally moved on to how to make it move a bit more gradually. Future episodes, we're going to take this code, we're going to expand this to provide some extra functions to make it easy to control several servos with one microcontroller, and how to add a bounce. So, looking at daisy chaining things, what we want to do is say, I want to move that, and I want to know when it's got where it's gone, because then I want to tell it to do something else. So, move to that position, move back a bit, then do that. So, effectively, we go all the way over there, we come all the way back, and then we do that, and just a little bounce on the end, but have that automatic. Might be useful for a signal. I've not needed it for points, but there we go. That's it for now. If you've liked that or found that any useful, comments, likes, shares, subscriptions, etc. as usual, more than welcome. In the meantime, I will leave you with that. I will hope you get back on with the rest of your day. I hope you enjoy yourselves. And yeah, we'll have a little, we'll be back with these. The next episode, I'm not entirely sure what we're going to be doing yet. I will think of something. Open to suggestions and comments if there's anything you particularly want to see. There's all sorts of stuff I've got left to do around motor control and other bits and pieces. Yeah, I'll catch you around. Thank you very much, and goodbye.